Alright, so we've already covered energy generation on a ship. Now it's time to consider energy storage, which, just to remind everybody, that would be like if we're going from this star to that star in the... Hang on, let me pull this up so I'm sure I get it right. I know it's the Hubble Space Telescope. Yes, it is the Eagle Nebula, Pillars of Creation. But the idea being that, hey, we're always going between those... Nope. These 2 points. Flat hands work a little bit better with the background removal. But we're always going between these 2 points. So if something is built up there, such as a space station or planetary colony, you have external power that your ship can go to and just recharge whatever its energy storage system is, as opposed to if you were to just be exploring out there where we're not really seeing many stars. In that case, you need energy generation because, generally speaking, energy generation has better energy density, greater energy density than any energy storage. The analogy I use is that a gallon of gasoline has more energy in it than a gallon of lithium-ion battery. There's mainly 2 that I want to talk about, mainly 2 energy storage mechanisms that I want to talk about, but just quickly going through, there's capacitors, which are pretty simple devices, and I do like them, but they're good for fast charging and discharging, not good for massive storage. Batteries, those better for larger storage compared to capacitors, slower to charge and discharge, and there are also issues like if they start on fire, they burn very long. And also some of how it's not as stable because you do have molecules, ions moving around, and there's the risk of dendrites forming, and batteries can go bad. Chemical energy storage, so that's different from chemical generation, where that would be like using artificial photosynthesis, where you take carbon dioxide, water, and energy, and you make things like methane, propane, or octane. You're making the hydrocarbons that you then burn. So it is kind of sealed. It's like, there's that, but it's nice and all, but, I want to talk about superconductors and superparamagnets, which superparamagnets does something I came up with. Superconductors, they really do exist, and they can be used for energy storage. Before getting to those, however, there is one other form of energy storage I want to mention, and truly, it is energy storage. It is not generation, and that's antimatter. So the idea being you have a hunk of antimatter, you have a hunk of matter. You put them together, and they have total conversion to energy. That, hypothetically, is the greatest energy density you can possibly have for storage. It is not energy generation, though, because antimatter, for our purposes, is not natural. It is synthetic. It must be created. It must be synthesized. Yes, technically, it is completely natural. Antimatter is created in the universe, but not in large quantities. Okay? Technically, should have been equal from the Big Bang. Should have had equal components, matter and antimatter. We don't know why matter won, why there is more matter, but it still is. We don't have large components there. You have to make it, which means you're investing the energy into it. So it is energy storage, because that's the energy you get out later when you combine it with normal matter. Okay, so yes, that is energy storage. Anyhow. Superconductors. So these are really neat. Superconductors are materials that normally... I got a wire here. Just a USB cable. But normally when electricity flows along this wire, there's resistance. So the energy that goes in on this side is less when it comes out this side. Now, true, we got plenty of good conductors, so it's, the energy loss is minimal, especially for like this. It's not that long. But in a superconductor, we can push that down to insignificant levels. The amount of resistance is insignificant. I'm not sure if... I think there might be some superconductors that do, in fact, get down to, no resistance, but I think there's others where it's a little bit more. And it could also be that there's actually no such thing as zero resistance. It's just very small. But a problem with superconductors, a lot of them, is that even the high-temperature ones, we're talking, you need liquid nitrogen. They're still cryogenic. But there's other superconductors that are not high temperature, where you're talking like liquid helium. Fractions of a degree Kelvin above, well, fractions of a Kelvin, technically they're not degrees, fractions of a Kelvin above absolute zero. So that's 1 Kelvin unit is the same as 1 degree Celsius. Whereas liquid nitrogen you can use for high temperature superconductors, those, and I should actually check. Yeah, give me one moment, I'll look it up. Yeah, so liquid nitrogen is negative 196 degrees Celsius or 77 Kelvin. Yeah, so that is still much warmer than like liquid helium that I mentioned. That is a fraction of a fraction of 1 Kelvin above. I don't feel like looking that up. I just remember it is very tiny. So yeah, that's better, but we want to get to room temperature superconductors. But anyway, coming back, how do you use a superconductor for energy storage? Well, you make a ring of it. And then you just put an electrical current with some voltage on the ring, and it just goes round and round and round and round. Just keeps going round and round. Because it is a superconductor, there's virtually no resistance. So that current will keep going round without any loss of energy, without the voltage coming down at all. So yeah, you can pump in a lot of energy on that, and it'll stay there as long as it remains a superconductor. And I feel like there was something I forgot to mention, but I'll just keep going. I'll think of it later if it was important. Oh, that's right, the Cooper pairs. So the way a superconductor actually is a superconductor is electrons normally, hey, they're like poles. So, they're both negatively charged, so they want to go away. But in a superconductor, the situation is correct, the conditions are correct for them to actually pair up. So they move together, as opposed to, like if you just had two freely floating electrons, they would resist coming together. But in this, no, they actually pair up and then they move together. And these pairs are called Cooper pairs. And it is actually this interaction, the Cooper pairs, within the interactions within the Cooper pairs, that allows them to travel in the superconductor without resistance. Now that's great. That's great, but there is a problem with it. Superconductors, and I can believe a lot of people don't know this, superconductors have a maximum amount of energy that they can store. If you go beyond that, you actually will lose power. Here's why. You got those Cooper pairs. They're moving around, right? They're going around in the superconductor. There's more than one of these. If you put too many in, so if you have too great a current and potentially also too great a voltage, I'm not certain of that. It's been a while since I'd seen this talked about. But they can actually start hitting each other. It's like there's only so much space in the superconductor, and the Cooper pairs, yes, for the most part, they are going without resistance. But it is possible for them to hit each other, for them to interact with each other, and those interactions between the Cooper pairs can actually basically cause spontaneous resistance. In which case, then you would lose energy because there's now resistance there. And potentially there could be even larger problems than that. Like I could see if that resistance were heat, what if you're now causing part of the superconductor to lose superconductivity? Not a good scenario. So you do need to keep below that overcharging limit with the superconductor. But it's still, these things are really neat. And yes, they do exist. Superconductors do exist. I'm not sure of any examples where they are using them for energy storage. But that is definitely something for decades now. It's been known we can do that. I just don't know if anyone has bothered doing it. Because if anyone's thinking, oh, well, wouldn't that be great in place of batteries in large-scale situations? Maybe, except you need a lot of the high-temperature superconductor material, and you need the cryogenic system to keep it cool. That might be why batteries are actually an easier option, because a lot of batteries, they just sit there, and they work. Battery. Still battery. Doesn't matter what technically it's temperature. If I get this thing too cold or too hot, it would cause problems, but at room temperature, no, it's fine. Can't say they're superconductors, so I could see it just being that kind of cost-benefit analysis. Anyway, now I want to talk about something that I came up with for my fiction for the Catherineverse, which is superparamagnets. There's quite a bit to talk about here, so hopefully hopefully I'll be able to keep this video short. We'll see. So, to understand what a super paramagnet is, I guess we need to talk about what actually makes a material magnetic. And that is, it's the electrons in there. Actually, a lot of fundamental particles have what's called spin. And if spin aligns, like all the electrons, their spins align in a material, it'll become magnetic. That's basically every electron is like a small magnet, small just bar magnet. And spin indicates, what direction the bar magnet is pointing in. If they all align, you have a magnet. You have a magnetic field that'll reach outside the material. And something like a ferromagnet, a permanent magnet, they maintain that alignment more or less indefinitely. For our purposes, we're going to say indefinitely. There are ways for a magnet to lose magnetism, but putting that elsewhere. A paramagnet is, here, I will come back to that. Then there's also, I think it's diamagnetism? I don't quite remember the term, but basically non-magnetic materials like, say, wood. In that, the electrons, the spins are all in whatever direction, so they don't coalesce, they don't align into one coherent direction, so you have no magnetic field. And it's also those electrons that are stuck askew, they don't align. They're not going to align. A paramagnet is something actually in between, where if you just have it sitting there, the electron spins don't align, they are askew. But if you expose it to a magnetic field, and let me turn this on, they do align and you get an induced magnetic field. So in this graphic, I'm doing things a little differently here. I'm actually putting it in the video right away instead of editing. But the just straight vertical lines, that's meant to be an external magnetic field acting on this paramagnet, while the circular field is meant to be, the circular field lines, those are the induced field, right? The magnetic field that's been induced. Yeah, so that's just basically how a paramagnet works, and these are real. A super paramagnet, I'm basically just saying that that's the reaction to the external magnetic field is very powerful. So technically, it should be producing a field I don't know if I want to say comparably sized, because that would mean that if you had like a star, it's a very powerful magnetic field, and that's, would produce such straight lines because it's very distant and very powerful. Technically, it would also be straight if it were 1-to-1. That's a bit ridiculous. But still, it would be a very powerful reaction. So the magnetic field would have a great deal of energy in it. The induced one would have a great deal of energy in it. Okay, well, how does that work for storing energy then? Especially because once a paramagnetic material or super paramagnet, it's just super in that it's a very strong reaction. That's all. Otherwise, it's just a paramagnetic material. Well, normally, you remove that external magnetic field, the paramagnet goes back to being from aligned to askew. So the magnetic field is lost. Okay, so how do we make sure that field stays there so it actually works for energy storage? With this keeper thing on there, that's the box around the square. So, and keepers are real things, and you do use them for ferromagnets, including like a horseshoe magnet. So, and I've done this before. So imagine you got, a horseshoe magnet. Now, I'll hold it this way. It looks better on the camera, but it's less comfortable to be twisted this way. So horseshoe magnet, you've got pole here, and it goes through. And if you hold something up, like plastic container, and this is what I've actually done, where here, plastic container here that holds iron filings, the magnetic field will hold it up against the screen. So, and you can see that, and I did this in front of a group of kids, they loved it and all that. What the keeper does, so we got that magnetic field coming out, just like in the image over there, where it's coming out of the material. Well, fun thing about fields is every time something crosses a field line, that is when you will see the energy change. Okay? Which is part of the reason why you want a keeper. Because right now, it's like you've got those iron filings. They're being held by the magnetic field because they don't want to move. They don't want to change the energy of the field. If they were to move, energy would move in or out of the field. Well, it's also, if that wasn't there at all, we just have the horseshoe magnet, there's a lot of stuff moving through the field, so we can lose energy. This is why this object is called a keeper, because you put it on there and it keeps the magnetic field safe. It keeps it from losing energy. And what it is, when I did this, it was just a piece of iron, a block of iron. Put it there, and what happens is that magnetic field that's going outside, the induced magnetic field here in this image that's going outside of the object, it goes inside, instead of it going through the atmosphere, it goes through that piece of iron, or whatever this material is. I just describe it as something with an extremely high magnetic permeability, which is important because that means the magnetic field wants to go through that material, and also it goes through it with very little resistance. So there's little energy lost just because the magnetic field is in this object. Technically, you could have material worse permeability that would see some energy loss, but for now, no. We got an idealized material here, at least idealized enough. Okay, so that means you can take this thing, the super paramagnet here, and here's the holder for it. So let's go like that. If it's out like this, now it can be exposed to an external magnetic field, such as from a star. As I already said, very powerful. Also planets. Planets have very powerful magnetic fields as well. Okay, so you have that there, it gets induced. Well, you just slide it into that keeper, and the magnetic field will now enter into the keeper because it wants to be in there, and now you can just leave it like that. Just leave it like that. And the magnetic field is going through the keeper and feeding back into the paramagnet, so it's not losing any energy. Pretty neat. Pretty useful. And magnetic fields can hold a lot of power. It's like, there's some neat stuff you can do with that. But it's also, one other thing that I should technically add here, I didn't put it in the graphic, maybe I should have, but you could also have, and you kind of need it, like here's the paramagnet again, you need something like down here, or maybe something surrounding it, that can produce an electromagnetic field. Because you also want the ability, well, you use that because if it can produce one, it might be able to absorb it. So you need something there that will absorb the energy out of the magnetic field once it's removed from the keeper. But you also want the ability to generate a magnetic field. So you want to be able to plug this into a battery, since I just have something. Plug it in there and then charge up the paramagnet, so that then, it's out, you're charging it up, can put it back in, you're good. So you're not limited to very powerful external magnetic fields for charging. You can instead just plug it into a space station or other ship to charge it. I'm just trying to think. Anything else to really mention here? I think there is one or two things. I just need to think a little bit on what those are. That's right. Yeah, I can turn that off though. There is no need to be concerned about overcharging with the super paramagnet idea, because basically once the electrons get perfectly aligned, that's it. You can't go beyond perfect. Quantum mechanics does allow for some weird things, but I don't think we need to be concerned about that here. But it's once they're aligned, that's it. You just need to maintain that alignment, and that's all you get. That's all there is to it. Unlike superconductors where there's an overcharging concern. Another thing that's advantageous with a super paramagnet versus superconductor is that because spin is just fundamental to a particle. Whereas you go to that superconductor, you got that current going there, it needs a voltage. That's when you plug it in, that is the energy that you're getting out of there, is the voltage. Voltage isn't exactly natural, in that it doesn't just exist as part of the electron. All right, it is, to put it another way, it is in an unstable state. The electron pairs are in an unstable state because they don't want a voltage. They want to go down to the lowest energy level, and that's an elevated one. So this is an advantage to super paramagnet because it is inherently stable. You're storing the energy not in this unstable state. Well, it is technically unstable, but it's the alignments that are storing the energy as opposed to the energy level of the electrons. So it is advantageous, and that is something that they actually do want to take advantage of with something called spintronics. And this is also part of why I thought of super paramagnets to begin with, is to have a magnetic counterpart to superconductors, at least for energy storage. So electronics are all based on voltage. So in order to record a 0, you have an electron at this energy level. To record a 1, it's at this energy level. And by the way, 0 is down here, so this is 0 still, down here is actually no energy. So even 0 has a voltage. There is energy there. Okay? But as I already said, electrons don't want to actually be at these energy levels. They want to fall down to 0, to actually 0. Not data 0. Here, let's actually say, let's change binary. So it's 1 and 2 instead of 0 and 1. No, I'm going to make that mistake. So it's data 0, data 1, and then this is like energy 0. Okay? So if you unplug a computer, a lot of things in it, it's volatile memory, because your RAM, the buffers within CPUs and GPUs and such, is volatile. So once you lose power, the electrons fall like that. It's non-volatile storage, such as flash and also magnetic hard drives. Those non-volatile, they actually do maintain those levels in some way. In a magnetic hard drive, it is by, hey, is the material at this point magnetic field up or down? So basically, are the electrons aligned spin up or spin down? It's kind of what you're doing there. Flash memory works on a very different principle. That's actually, look it up sometime. It sounds like science fiction. It isn't. It isn't. But it is actually using, at least I'm pretty sure I'm remembering this. It has been some years. But it's basically using quantum mechanics to store data. It's really, really neat. But spintronics, because it's based on spin, as I said, it's an innate property of an electron. So as long as you don't have something that's going to cause the spin to flip, spin up is 1, spin down is 0, you lose power, it's still spin down, or it's still spin up. So spintronics will inherently be non-volatile. Or at least that is the goal. We're still working towards making sure that the electrons can move around without turning, without flipping, but once we achieve that, once it's actually like, hey, we have something that can compete with the electronics, that can be the successor to electronics, once we're at that level, we're talking about something that is inherently non-volatile, which also is a huge advantage, because, like, I'm using my laptop here. A lot of people, they really like the whole instant on, instant off. That's what spintronics would give you. You power it on, you can be right back where you were. You turn it off, it just loses energy, but all those electrons, all those spins, they're still where they are. So it just comes straight up right away. It's just, hey, I'm moving again. So, yeah, and it's, I've seen that. I've seen some other things that are not coming to mind, that we're investigating alternatives to electricity, electronics, by, these alternatives, we're looking at magnets, and we're finding that magnets and magnetism can provide a lot of advantages that we don't have with electricity. Now, there are also some caveats to that that can make it where it's like, yeah, we can do that, but it's harder to achieve. But it still is, like, we can have higher data storage densities, we can have better data. The energy to encode data can be far less when we're using magnets. It's really neat. And that's part of the reason why I want a counterpart to superconductors. It'll be magnetic. What kind of advantages does it have? Various things like that. It's technically more stable because it's spins, which are the alignment of spins, which are just innate to the electrons. But there are the disadvantages in this case, such as, well, here, I'll turn it back on. With this, there needs to be something to absorb the energy from the magnetic field as it's withdrawn, but there's also, you need the ability to produce a magnetic field to induce one on there if you don't just go to a star or something. Superconductors don't have that. Superconductors are like this battery. You just plug it in and you're good. You go. Both for charging and discharging. So there are definitely still advantages to superconductors. And indeed, the ship in a letter from Catherine, where I do get more into this stuff, how this works, it uses both. Because there are instances where this is better than that. And it's like, hey, we'll just have it all there. One is superpair magnets, pull up to a star, pull it out. It gets an induced field, slide back in, you've just recharged. Can't do that with a superconductor. But a superconductor, if you can pump the energy in there, like let's say, you're just moving in and out the superpair magnet a few times, so that you're inducing the field and then you're using the thing to absorb the energy out, pumping that into superconductor will probably discharge faster into your system than the pair magnet. But it still is. the whole, yeah, it's advantages and disadvantages to both. Have them both. Use them both. And it also helps the superpair magnets fiction. So I can just say it works this way. It is bending laws of physics, though, I'm pretty sure. I am taking things that do exist and putting them to an extreme. So who knows? Maybe one day it'll be made. Kind of doubt it, but you never know. All right. Yeah, that I think covers it. And I haven't really thought of any other energy storage mechanisms there. But is just coming back here. Turn that off. Just coming back to the point though about why even consider energy storage when there's energy generation means because sometimes if you just need to go from here to here, it's all you need. It's very simple and might be easier and cheaper. So why wouldn't you? You got to think about, okay, what do I actually need? And that applies not just in fiction. All right. See you next time.